So as for the analysis, of course, we've got our R out taken from there, and our R in looking into there. R in looking into there. So let's start by coming up with the R in, because we're looking from the emitter, we're looking into the transistor like that. Because we're looking inside through the emitter. So when we look into the emitter, our R in will be how much resistance or impedance we see inside. R in will be nothing but Re, because the only resistance we see will be Re. Our R out on the other hand is still Rc in parallel of R out, because we still have, in a non-ideal case, Ro there. When it comes to the gain, unloaded gain first, is still V out over V in, and our V out, which is the voltage at that point, is still IC. By the way, we have to put IE. So IB and IC combine to make up IE. As you can see now, the input is on the emitter, so the current there is IE, the output is on the collector, current is IC. They are all both of the same direction, so we've got a positive gain this time, and that will be, our output is on the collector side, IC R out, and the input is on the emitter side, IE, which is flowing through IE, which is flowing through RE, basically, which is flowing through RE. And that is the unloaded case where we don't consider RS. So in that case, we've got, we know IC over IE is alpha. That will be alpha RC in parallel of RO over RE. An alternative to that would have been, AV out would have been calculated as, beta IB divided by times RC in parallel of RO divided by beta plus 1 IB RE. These two will cancel. IB will cancel that. Beta plus 1 is still there. And that's what is creating the alpha, actually, RC in parallel of RO over RE. Now, we also know that that RE can be computed as R pi divided by beta plus 1. Going from that, and we substitute that into the equation, we would get basically beta over beta plus 1 if we put back the value of alpha, RC in parallel of RO divided by RE, which is R pi divided by beta plus 1. Very important. So that way beta plus 1 will cancel with beta plus 1. Beta over R pi, which is GM, would lead to GM RC in parallel of RO. So in an ideal case, one would have, in an ideal case, one would have the unloaded gain to be simply GMRC, because and that will be ideal of common base, of course. That is because RO will be infinite. GMRC, okay, and that will be the unloaded gain. What about the half loaded gain and the fully loaded gain? Let's start with the fully loaded gain. When it comes to the fully loaded gain GV, or AV fully loaded, meaning RS considered as well as R in, one will get it to be equal to the open loop gain, which we know is GMRC in parallel of RO in the non-ideal case, but GMRC in the ideal case. All of that multiplying the impact of the load on the load, as well as output loading factor, impact of the load, which is RL over RL plus R out, as well as the impact of the rs, which is captured through the input loading factor, which is rin over rin plus rs. So if we do that, so now this will lead to gm r out, because rc in parallel of ro is r out actually, times rl divided by rl plus r out, all of it times r in, which in our case is re, re plus rs. Now, as we know, when we've got two resistors in parallel, they actually give 1 over r1 plus 1 over r2 to the power minus 1. If you develop this further, you normally get, put on the same denominator, you get r1 plus r2 divided by r1 r2 to the power minus 1. That normally leads to the product of the two resistors over their sum, which is exactly what we have here. We've got r out times rl divided by rl plus r out. So that basically, that is actually r out in parallel with rl. So that's why the fully loaded gain of a common base amplifier, or the one we're analyzing, will be summarized to gm r out in parallel of rl, and this is the non-ideal case, times re over re plus rs. And in the ideal case, where r out is just made up out of rc, that will be gm rc in parallel of rl times re over re plus rs, is provided in the notes. Okay, now you know where it comes from.